let's look at example 2 of the power functions handout. It says example 2, for each function state the domain and range, describe the end behavior, and identify any symmetry. Alright, before we continue on with that, I would simply like to mention that I hope you had a chance to watch and make some notes of the videos from the Khan Academy on intervals and interval notation, and also polynomial end behavior. So if you haven't had a chance to do that, I suggest you do that right now. And if you have, then let's just I would simply like to mention the following. When they talk about end behavior of a function, when we want to describe the behavior of a function, we normally do it in the context of the quadrants of the Cartesian plane. So if you may recall that the Cartesian plane has 4 quadrants and they are labeled as 1, 2, 3, and 4. So for example, if we were dealing with a cubic function, we say that it's moving from quadrant 3 to quadrant 1, or more precisely, if we're dealing with a odd function, then we're moving from quadrant 3 to quadrant 1, and if we're dealing with an even number function, with an even degree function, then we're moving from quadrant 2 to quadrant 1. And of course, we know that if the coefficient was negative, then this would change. Say for an even function, will be from quadrant 3 to quadrant 4, and then also we would be going the other way from quadrant 2 to quadrant 4 for an odd number function. Okay, well, this is kind of messy, but I think if we start looking at these examples, everything will make more sense. Okay, so example 2, we have this. It says that for each function we should state the following criteria. So state the domain and range, describe the end behavior, identify any symmetry. So we're given y equals negative x, and let's state the domain and range. So the domain and range for this function, as it is pretty clear, we look at the set of x values and we say that the domain belongs, that x belongs to a set of real numbers and there are no real conditions. And then the range, right, that's the domain, sorry. Now the range is the same thing. The range is y belongs to a set of real numbers. Okay, straightforward for this domain and range for this function. Now describe the end behavior, as we said before, right? And I'm gonna have maybe the quadrant here as a reference. Basically this is quadrant 1, 2, 3, and 4. So we can say that the function is moving from quadrant 2 to quadrant 4. Quadrant 2 to quadrant 4. Okay, from quadrant 2 to quadrant 4. And we can also say, if we use the notation of x approaching infinity, we can say that as x approaches negative infinity, comma, y also, well, y approaches positive infinity, right? So if you look at the values of x, and if you keep on going all the way to negative infinity, we can see that the y value is approaching positive infinity. And we can also say that as x approaches positive infinity, let's move this up a little more, y approaches negative infinity. Okay, and is there any symmetry on this? Yes, because it's because it is an odd degree function, we know that there is a point of symmetry around the origin. So we can say that there is a point of symmetry about the origin. Great, let's look at example 2. Example 2, we have this function. We're all familiar with this. It's a quadratic function, and the same idea, right? If it helps you, just label the quadrants 1, 2, 3, 4, and the first question, state the domain and range. So you may want to pause once again this video. What's the domain of this? Well, we know that the set of x values belongs x belongs to a set of real numbers, right? To all of them, there are no exceptions. This keeps on moving infinitely. How about the y values? Well, it doesn't exist below the x-axis, only above the x-axis, so we know that y belongs to the set of real numbers such that y is bigger than or equal to 0. Good. Now let's look at to describe the end behavior. Okay, so this is an even degree power function, so it's moving from quadrant 2 to quadrant 1. So it's moving from, and I'm going to abbreviate it now, from quadrant 2 to quadrant 1, Q2 to Q1. You can write it this way too if I ever ask you a question like that. Okay, it's moving from quadrant 2 to quadrant 1, and then you can say that if x approaches, as x approaches negative infinity, that is supposed to be an infinity value, sorry, I need to work on that. Anyways, as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, yeah, better job there, y approaches positive infinity. And number 3, because we know it's an even degree power function, we know that there is a symmetry of a line of symmetry in the y-axis. So line of symmetry in the y-axis. Okay, now let's look at our last example, and in fact I want you to try this yourselves. Maybe pause the video and see what you get for this. Alright, so this is the answer. Okay, good. So first, the domain as x, well, the set of x values, so x belongs to the set of all real numbers. Very similar for the range, since we know it's an odd numbered power function. These are the common domain and range for odd powered functions. In this case, it's a cubic function. We know that it moves from quadrant 3 to quadrant 1, and once again, if you find it helpful, just label the quadrants. We can see it moves from quadrant 3 to quadrant 1, and we know that as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y also keeps on getting positive. And of course, we know that there's a point of symmetry about the origin, so we can take half of this, go around 180 degrees, and we get the other half.